All right, let's solve this question. So what it's first asking us to find is initial current, right? How do we find initial current? Well, we know that the switch has been closed for a long time, right? At t equals 0, it changes, but it's been closed for a long time. Now, whenever you see that long time, all right, always think DC, all right? This means the condition is a DC conditions, right? So what do we know about the inductor at DC conditions? Well, it just turns into a short circuit, right? So we can get rid of the inductor, we can draw a line, boom. What do we know about t equals, before t equals 0 about the switch? Well, the switch was closed, right? So we can even draw a line there. All right, there we go. So here's our circuit for the longest time. This is how it is. Now we have to find this current, right? Now, here's the thing, and I just want to demonstrate to you. So let's take this over here, and let's source transform it, right? So we get rid of this. We turn this into a current source. You know, this is a current. It's 5/2 amps, right? We get rid of this. We move it so it's over here, right? Now, here's the deal, right? We have this current. It goes up here, and it enters this node, right? Now, it can go 1, 2, 3, or 4 different ways. But all of these ways have resistance except for this way. This direction has no resistance, which means we know that all the current is going to go through here, like that. None of the current's going to go here, none of the current's going to go here, and none of the current is going to go here. So we know that IL of t is equal to 0. Now, if that didn't make sense, that's fine. You could also, if you really want to, you could do a KCL over here, right? But what you're going to find in the KCL is all you really have is a resistor. You don't have any voltage here. You don't have any voltage here. So there's literally no current, right? There's no current flowing through this. If you look at the solutions, that's what he does. He does a KCL here and he finds the exact same thing. There's no current here. But this is the more like theoretical, like why that happens, if that makes sense. So what do we know? There's no current, so it's 0 amps. All right, easy enough. Now let's find the current through the inductor. This one's a little bit more tricky. Not too bad though. Let's look at it. So we want to find the current through the inductor, right? Basically, we're just trying to find this equation. How do we do that? What is this equal to? Good question. Let's figure it out. So first of all, let's figure out what we know already, right? The thing is, now we know that time is greater than 0, right? Which means this switch opened up, right? So what we can do is we can actually just get rid of it. So let's just do that. Let's get rid of this thing over here. Boom. Okay, so now that that's gone, let's look over here. What we need to find is ILT is equal to what? And the good thing is that in our cheat sheet, we actually have this equation right here, and it's there for us to use. But to use this equation, or this one, these both are the same thing. To use either of these equations, we need to get the circuit in this form, which means, that's right, we need the Thevenin equivalent. So let's find our Thevenin equivalent. So let's find the resistance first, because that probably is going to be easy. So THEVININ, there we go. Okay, so what's the resistance that we're looking for? Well, how do we find RTH? Well, again, we turn off all the independent sources, so we have to turn that off, and then just find the equivalent resistance, right? So let's do that. So let's turn off this source over here. Let's add in our 2K resistor. Let's add in our other 2K resistor and our 1K resistor. Okay, here's the thing. Normally, when we find RTH, we could put a voltage source over here, connect it up, trying to find the current, We don't need to do that, though, because all this is resistors. All we're doing is simplifying this, right? So that's easy. We don't have to do all the hard work. All we have to do is simplify this. So how do we simplify this? Well, let's look at it like this. And this actually helps me when I'm visualizing it to just redraw it a little. Split it out. All right. So what we have is we have one resistor going into two parallel resistors, right? So we can draw it like this, one going into two, right? All we have to do is combine these two parallel resistors first, right? So how do we combine them? Well, I should leave it there. Okay, how do we combine them? Well, we can use this equation, right? 1/1/2 plus 1/2, which is equal to 1/1, which is equal to 1, right? So we know that these two resistors, they combine to be just a 1K resistor in series, right? Like that. Now here's the thing. We know that these two are in series, which means we can combine it even further and just say that RTH is equal to 2k ohms. All right? Okay, pretty straightforward. Now, let's find the Thevenin VTH. All right, that's the last thing we need. So how do we do that? We have to have an open circuit on these ends, right? So let's just do that. Let's add in our voltage source. Let's add in our 2 kilo ohm resistor, our other 2 kilo ohm resistor, our 1 kilo ohm resistor. Now here's the thing. We're trying to find voltage across these 2 points, right? That's going to be our VTH. I'm going to use shortcuts and speed through this. You can use, KVL, whatever's easiest for you, but these shortcuts just make the most sense to me. All right, let's add in our ground here to make things easy, right? Since our ground is here, this becomes a super node, which means we know this point is 5 volts, right? The thing is, we know that there's no current going this way, right? The current here is 0 because this is an open circuit, right? So that means there's no voltage drop across this resistor, right? Which means we could literally just get rid of it entirely. Like, it doesn't even matter. Okay, so now we know that we have 2 resistors in series. So the voltage is going to drop exactly halfway here and another halfway here, right? So that means this point is just going to be 5 over 2. It's just going to be 2.5 volts. Again, if you want to, you can do KVL, you can do the math with these resistors. I just find this shortcut the easiest because these are the same thing, right? So the voltage is going to drop halfway here and another halfway this way, right? Yeah. So anyways, so we know that it's 2.5 volts over here. Since this is 2.5 and this is 0, VTH is equal to 2.5 volts, right? Cool. So now we have our Thevenin circuit. So let's draw that out. So we have our 2.5 volts over here. We have our resistor. What was our resistor again? 2 kilo ohms. And we have our little inductor. Cool. So what do we do next? Well, what we can do is we can use the cheat sheet equation now. So I'm going to use this bottom one, and you can use the top one and just plug in values for V and R. You're going to get the exact same thing. I'm going to use the bottom one because that's the one that they use in the solutions. So that might make a little more sense if you're looking at those. So here, this is our magic equation. We just plug stuff into that and it works. So let's do that. I of LT is equal to, okay, now we need to know what it is as it goes to infinity, right? How do we find that? Well, here's the thing. If you notice, this, we can transform this, right, into an equivalent Norton circuit. So let me just delete this for a second. We can literally use, Norton equivalent and transform this so that it becomes a current source in parallel with a resistance and in parallel with the inductor, right? And what do we know about this current source? Well, V is equal to I over R, right? I over R, right? So that means that this current source is going to be 1.25 amps, right? So we know there's 1.25 amps going this way. At DC, again, at DC, this thing becomes a short circuit, right? So this literally is going to be a short circuit. So we know, ignore that. So we know that there's 1.25 amps going this way. There's some resistance here, and there's no resistance here, which means all of the current is going to go this way, which means all of the 1.25 amps is also going to go into the inductor, right? So we can know for sure that this is equal to 1.25 amps, which is equal to our I of L at infinity, right? Pretty straightforward. So we know that that's what that is. So we can continue plugging in. I of L of T is equal to, what did we say it was? That's right, 1.25 amps plus, what is it at 0? Remember, we found that in the last part. We know it's 0 minus, same thing from earlier, 1.25 amps. Actually, it's milliamps. I had the units wrong on this one. It's milliamps. Same number, but milliamps. Okay. And then e to the negative T, R, L, right? Now, what are R and L? R and L are just the resistance and the inductance, right? So resistance we know is going to be 2K, and the inductance is going to be 100 milli, right? So this is our final equation. We can simplify it a little. We know that, these are the same numbers, so we could also write it as 1.25 milliamps times 1 minus e to the negative T2K over 100M. All right. Now, here's the thing. In the solutions, they simplify this down to 50 micro and they put it on the bottom. You could do that. You could leave it in this form. Technically, this and the solution are the exact same equation. And yeah, so that's our answer. So I'm going to leave it like that and say our answer is 1.25 milliamps times 1 minus e to the negative t times 2,000 or 2K over 100M. And yeah, that's our solution.